This video will cover our lecture for the atomic structure and the periodic table. I'm going to start off by asking you, what is matter made of? We went over this last week. Matter is anything that takes up space and has mass, right? So that comes down to the basic unit of matter are atoms. So how do we classify matter? I'm going to go over this chart with you. Matter, we said that it's anything that occupies space and has mass, right? So matter can be broken down into two groups. We have the pure substances and we have the mixtures. Pure substances cannot be further broken down, so they're fixed composition. And with pure substances, when you mix them together, you can have mixtures, right? So mixtures are a combination of two or more pure substances. So how do we go from mixtures to pure substances? We physically separate them. Pure substances can further be broken down into elements and compounds. What are the difference? Elements, they cannot be subdivided by chemical or physical means. So those are like chlorine or helium gas. Another example can be pure gold. And then if you chemically combine these with other elements, you can form compounds. What are compounds? An example, table salt is a compound. It's an NaCl. You see how we have the sodium and the chloride. That makes the table salt, sodium chloride. Going into the mixtures can be broken down into two units. We have the homogeneous mixtures and the heterogeneous mixtures. So the homogeneous matter is a uniform composition throughout. That's an example I can give you is like if you put sugar in a hot cup of coffee. When the sugar dissolves, it becomes uniform. And then we have the heterogeneous matter, which is non-uniform. So that's like a bowl of cereal and milk. You know, they don't uniform. So let me go over an element. Element is a substance that consists of identical atoms, right? So we have a hydrogen, carbon, iron. Another example would be neon gas. In total, we have 118 known elements. And 98 of these 118 known elements occur in nature. The 20 remaining are made in laboratories. The list of these known elements with their symbols can be found on the periodic table. Next, I'm going to go over compounds. Compounds are a pure substance that's made up of two or more elements in a fixed ratio by mass. Properties of compounds are different from those of a mixture of its constituent element with no resemblance. For example, for water, water is made out of hydrogen and oxygen. If you look at the densities of water has a density of 1 grams per milliliter. And then hydrogen has a density of 0.084 grams per liter, and oxygen is 1.33 grams per liter. All of these are at room temperature. So there are about 20 million compounds, but we will only go over a few of them in our class. We characterize compounds by its formula. This formula gives you the ratios of the constituent elements and identifies each element by its atomic symbol. Let's do an example here. So we have table salt again, NaCl. Table salt is also known as sodium chloride. Sodium is the Na, chloride is Cl. So we see that we have one Na, sodium, and one Cl, chloride. So the ratio of sodium atoms to the chlorine atoms is 1 to 1. Another example here is water. Water is known as dihydrogen monoxide. So di means 2, hydrogen, mono means 1. So we can see that we have 2 hydrogens and 1 oxygen. So the ratio of the hydrogen atoms to the oxygen is 2 to 1. Do you guys see how the number 1 in these ratios are omitted? So you do not write H2O1. This is incorrect. Here says the formula gives the atomic symbol of each element combined in the compound, and the subscript gives the ratio of its constituent element. I just went over that. So let's do a problem here. Problem 1 says, in the compound magnesium fluoride, magnesium is Mg and fluorine is F, combined in a ratio of 1 to 2. What is the formula of magnesium fluoride? Okay, so we know that the ratio is 1 to 2. First we have the magnesium, which is 1, and we have the fluorine, which is 2. So how do we write this? We write this as Mg F subscript 2. Problem 2. Says, write the formulas of compounds in which the combining ratios are as follows. We have sodium, chlorine, and oxygen, ratio of 1:3. So how do we write that? Sodium is Na, chlorine is Cl, and oxygen is O. So how do we write this? We have 1 sodium, 1 chlorine, and 3 oxygen. So oxygen sub 3. Our part B of problem 2 is aluminum and fluorine. I spelled fluorine wrong here, but that's okay. So aluminum is Al, fluorine is F. So the 1:3 ratio would be Al F to sub 3. Now I'm going to go over mixtures. Mixtures are a combination of 2 or more pure substances. Difference between compounds and mixtures is that the ratios by mass of the elements in the compound are fixed, whereas in a mixture, the pure substances can be present in any mass ratio. Here's the same examples I went over before. We have the heterogeneous mixture, a bowl of cereal with milk. They're not uniform. And then you have the homogeneous mixtures, like a cup of coffee with sugar or cream. When it mixes, you cannot separate them. That's a uniform mixture. Keep in mind here an important point. Blood looks like a homogeneous mixture, but it actually is heterogeneous. If you look at blood sample through a microscope, you can see that there's liquid and there's suspended particles. These particles are, you got your red blood cells, white blood cells, your platelets. Those are all seen under a microscope. So therefore, blood is not homogeneous. It is a heterogeneous mixture. Now I'm going to go over atomic theory. This was done by John Dalton in 1808. The theory stated that first, all matter is made up of very tiny indivisible particles called atoms. 2. All atoms of a given element have the same chemical properties. Conversely, atoms of different elements have different chemical properties. 3. In ordinary chemical reactions, no atoms of any element disappears or is changed into another element. Number 4 says compounds are formed by the chemical combination of two or more different kinds of atoms. In a given compound, the relative number of atoms of each kind of element are constant and are most commonly expressed as integers. 5 states that a molecule is a tightly bound combination of two or more atoms that act as a single unit. Dalton's theory is based on the law of conservation of mass, which states that matter can be neither created or destroyed, and by the law of constant composition, which states that any compound is always made up of elements in the same proportion by mass. So here's an example. Carbon monoxide molecule reacts with a lead oxide molecule to give a carbon dioxide molecule and lead atom. We see here. So we have one carbon, one oxygen, one lead, and one more oxygen. So we actually have carbon 1, oxygen 2, lead 1. And if we look on the product, we see that we have our two oxygens, we have our single carbon, and our lead. So we get whatever we started off with, we have the same amount at the end. Stating here, all the original atoms are still present at the end. They have merely changed partners. Hence, the total mass after this chemical change is the same as the mass that existed before the reaction took place. Let's do an example. If you decompose water, you will always get 8 grams of oxygen for each 1 gram of hydrogen. The mass ratio of O to H is always 8 to 1. So we know that water is H2O, right? So we have an oxygen and we have 2 hydrogens. The mass of oxygen is 16, hydrogen is 1. So looking at this, when we divide this in half, right, for each hydrogen, we're getting half of the oxygen, so that would be 8.0. I'm going to go over monatomic, diatomic, and polyatomic elements. Monatomic elements are single atoms that are not connected to any other elements. So we have, for example, helium, neon, hydrogen, fluorine. These are all monatomic elements. You have diatomic elements. Di here means 2. Diatomic elements contains 2 atoms in each molecule, and these are connected by a chemical bond. There are 7 elements that occur as diatomic elements, and they do not exist as free atoms. These 7 are oxygen, appears as O2, hydrogen, H2, nitrogen, N2, fluorine, F2, chlorine, Cl2, bromine, Br2, and the last one is iodine, which is I2. Then we have our polyatomic elements. Those contain more than 2 atoms in each molecule. So an example is the ozone, which is O sub 3. Another example is diamond. Diamond has millions of carbon atoms all bounded together in a gigantic cluster. So it would be carbon some unit. I'm not sure exactly how many millions are bounded. Something interesting to look up for though. So what are atoms made of? Atoms are made of 3 subatomic particles. We have protons, electrons, and neutrons. I have a lot of typos here. Neutrons. So protons have a positive charge. Their mass is very, very small. Because their mass is so small in grams, we have a different unit here that we use. It's called the atomic mass unit. It's abbreviated to an AMU. 1 AMU is equal to 1.6605 times 10 to the minus 24 grams. So our protons, which have a positive charge of 1, can be rounded to one significant figure mass of 1 AMU here. Our protons are found in the nucleus. Then we have the electrons. Electrons have a negative charge, and they are very, very, very small compared to the size of a proton. So if you look at the mass in AMU, it's 0.0005. Electrons are found outside of the nucleus. And lastly, we have neutrons. Neutrons have no charge. They're neutral. Their mass is very close to a proton. So when you round them to one significant figure, you also get the 1 AMU. The neutrons are also found in the nucleus along with the protons. Some side note here, it takes approximately 1,837 electrons to equal to the mass of 1 proton. So that can, you can kind of visualize that a proton is extremely bigger than an electron. Another note here says that like charges repel and unlike charges attract. So if you have a positive, they will repel. Negative, negative, they will repel. But if you have a positive and a negative, they will attract to one another. So we know that neutrons have no charge, therefore neutrons neither attract nor repel each other or any other particles. So protons, neutrons, and electrons make up an atom. we know that the protons and the neutrons are found in the nucleus, which is the center of the atom, as shown here. This is the nucleus, center of the atom. And then all this cloud space is where the electrons can be found. Now I'm going to go over mass number. Each atom has a fixed number of protons, neutrons, and electrons. A mass number is the sum of the protons and neutrons. So you add the value of protons and the value of neutrons and you get the mass number. Problem 3 says, what is the mass number of an atom containing 58 protons, 58 electrons, and 78 neutrons? So we know that mass number is equal to protons plus neutrons. So for this atom, we will have 58 plus 78, which will equal 136. That will be the mass number of this atom, whatever atom it is. Then we got atomic number. Atomic number is the number of protons in the nucleus. On the periodic table, the atomic numbers are 1 through 118. So 1 through 118, excuse me. Each atom has a specific atomic number. Side note here says, if you know the atomic number and mass number of an element, you can properly identify it. So let's do an example now. It says, element with 6 protons, 6 electrons, and 6 neutrons has an atomic number of 6 and a mass number of 12, right? Mass number is protons plus neutrons. 6 plus 6 is 12. The element with the atomic number 6 is carbon. Carbon is shown on the periodic table as the letter C. Because its mass number is 12, we call this atomic nucleus carbon 12. So we write this as C 12 6. So C is the symbol of the element. I just went over is the mass number, and 6 is the atomic number. Problem 4 says, determine the atomic number of the atom containing 58 protons, 58 electrons, and 78 neutrons. So atomic number is what? We said atomic number is number of protons. This happens to be 58. Then it says, which element of the periodic table identifies this atomic number? I uploaded the periodic table for you guys to look at, so if you can pull that up, I'll wait a few seconds. Okay, so atomic number 58 is which one? Atomic number 58 is cerium. The symbol is Ce. So if we write this, Ce has an atomic number of 58, and the mass number is 136. Next, I'm going to go over isotopes. Isotopes are atoms with the same number of protons, but they have different neutrons. All isotopes contain the same number of protons, same number of electrons, but they have different number of neutrons. Because they have the different number of neutrons, their masses will be different. Remember, the mass number is protons plus neutrons. So if the mass is different, if the neutron is different, then the mass will be different. An example here is carbon 12, carbon 13, carbon 14. So carbon 12, well, first of all, we know carbon has atomic number of 6. So if we do carbon 12 here, that will be 12 minus 6. We'll get 6 neutrons. Carbon 13 will do 13 minus 6. That'll give us 7. And then carbon 14, 14 minus 6, that'll give us 8. So do you see how the neutrons are different? Therefore, the masses are different. We can write this carbon 12, carbon 13, carbon 14. They have same atomic number. Problem 5 says, how many neutrons are in each isotope of oxygen? Write the symbol of each isotope. We have oxygen 16, oxygen 17, and oxygen 18. So oxygen has atomic number of 8. So if we have oxygen 16, that would be 16 minus 8, 17 minus 8, and 18 minus 8. So what do we get? 16 minus 8 is 8, 17 minus 8 is 9 neutrons. (18 minus 8 is 10 neutrons. We can, the symbol for oxygen is O. So we have for oxygen 16, and then for oxygen 17, and oxygen 18. Most elements are found on Earth as mixtures of isotopes, and the atomic masses for different isotopes, we get them by taking the average. This says here the atomic masses and isotopic abundances are determined using an instrument called mass spectrometer. If you decide to continue on with the chemistry course, and if you take organic chemistry lab, you will use a mass spectrometer, I think. I'm not sure. Next, I'm going to go over atomic weight. So the atomic weight is the weighted average of the masses in AMU of the isotopes, which I just mentioned. So we have an example here. 2 isotopes of chlorine exist in nature, chlorine 35 and chlorine 37. The masses of chlorine 35 atom is 34.97 atomic mass unit, and the mass of chlorine 37 atom is 36.97. So we see here that the mass in atomic mass unit is very close to its mass number. That is because if you remember beginning of the lecture, we rounded the atomic mass unit to one significant figures. It was like 1.00097 or something. That's why there's that difference and they're not completely identical. So 75.77% of chlorine is found on planet Earth as chlorine 35 isotope, and 24.23% of chlorine is found as chlorine 37 isotope. So the atomic weight of chlorine is to take the average. So how do we do this? We have 75.77 out of 100 times chlorine, let me move up here, chlorine 35, which is 34.97 AMU, and we add the 24.23% of chlorine 37, which is 36.97. So when you calculate this, you will get 35.45. If you look up this on the periodic table for chlorine, the box for Cl is number 17. It should say on the bottom 35.45, something, maybe 2 something, I think. So this bottom number is the atomic weight. A side note here, gold, fluorine, and aluminum occur naturally as one isotope, so it's just one. They didn't take the average. Problem 6 here. The natural abundances of the 3 stable isotopes of magnesium are 78.99% magnesium 24, 10% magnesium 25, and 11.01% of magnesium 26. Calculate the atomic weight of magnesium and compare your value with that's given in the periodic table. So same way, we have 78.99% times the AMU, 23.98. Let's just round it up, 23.99 AMU, plus we have the 10% magnesium 25, which is 24.99 AMU, plus 11.01% magnesium 26, which is 25.98 AMU. So when you calculate this, you will get 24.31 AMU. And if you look on the periodic table, the periodic table value should be 24.3050. Okay, the mass and size of an atom. The mass and the size of an atom are like a baseball and a baseball field, but imagine the field in a sphere that's like 1 mile in diameter. So the baseball is extremely small compared to the field, right? That's like the nucleus. The nucleus is very, very, very small compared to the size of the atom. Because the nucleus has such a relatively large mass, remember the protons and the neutrons are all in the nucleus. That's why it has a very high density, because the majority of the mass is in the nucleus. Let's go over the origin of the periodic table. A guy named Dmitry Mendeleev arranged the known elements in increasing atomic weight, beginning with hydrogen. So when he arranged this, he discovered that when the elements arranges in the order of increasing atomic weight, certain sets of properties recur periodically, then arranged into periods. So those are your horizontal rows. And then he discovered later on that the vertical columns, which are called families or groups, also have similar properties. So if we look at the periodic table here, we have the main group elements, which are groups 1A, 2A, 3A to 8A, which 1A, 2A, 3, 4, 5, 6, 7, 8A. These are your group A main group elements. Then you have your transition elements, which are the group B elements. I say here the IUPAC 1, 2, 13 to 18 is because they rearranged the numbering and it started to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. So a 3A is also 13 group. There are 3 classes of elements. As you can see, we have the metals in orange, metalloids in blue, and the nonmetals in green. Let me go over what each one of them are. Metals, excuse me. Metals are elements that are solid at room temperature, except for mercury. Mercury is found liquid at room temperature. Metals are shiny, they conduct electricity, they're ductile, they can be drawn into wires, they're one other important thing to know about metals is that they give up electrons. And we have the nonmetals. Nonmetals are different than metals. They accept electrons, unlike the metals, which I said they give up electrons. There are 18 nonmetals elements. They're mainly found on the right side of the periodic table, except for hydrogen. Metalloids, which are found here in blue. So they have some properties of metals and some properties of nonmetals. There's only 6 elements that are classified as metalloids. So, side note here, not only do the elements in any particular column, either group or family, of the periodic table share similar properties, but the properties also vary in some fairly regular ways as we go up or down the column. Let's say if you go down the column, the temperatures will decrease. Like, you'll never have an element that is misplaced. Everything will be in order. If you go from, let's say, you're going from helium to neon. Sorry, I don't know why I said helium. That's so weird. Helium to neon. Let's say you lose your temperature or you gain a temperature. Same thing will happen from going from neon to argon. So the alkali metals are all the group 1A elements on the periodic table except for hydrogen. The reason hydrogen is placed there is because it only has one atomic mass of 1. And you have your halogens, which are the elements in group 7A of the periodic table. These are your halogens. And then we have the noble gases. And those are group 8A. These are your noble gases. So how are the electrons in an atom arranged? We ask ourselves, are these atoms arranged randomly, like for example seeds in a watermelon, or are they organized into layers, like layers of an onion? In 1913, Bohr discovered that the lowest possible energy level is called the ground state. So if an electron is to have more energy than it has in a ground state, only certain values are allowed. So values in between are not permitted. We call this, the atom is quantized. In order for me to explain this to you, there's an example of walking up a flight of stairs. So you can only put your foot on any stair steps. You cannot stand in a place between the two steps, right? Either you can step up or you can step down. There's nothing in between them. This is the best way of explaining how quantized works. So one conclusion reached by Bohr is that the electrons in an atom do not move freely in a space around the nucleus, but rather they remain confined in a specific region of space. And this space is called shells. There are maximum 4 shells. So on shell number 1, you can have a maximum of 2 electrons. The shell number 2, you can have maximum of 8 electrons, and 3, 18, and so forth. So electrons in the first shell are closest to the positively charged nucleus. I want to show you here. So here's sodium. This is the nucleus. So the first shell that holds maximum 2 electrons, so 1 and 2, is the closest to the nucleus. You guys see that? And then the next shell, which holds maximum 8, if you guys see 1, 2, 3, 4, 5, 6, 7, 8, that's shell number 2. So the electrons in higher number shells are further from the nucleus and are held less strongly together because they're not as close to the nucleus. Remember, the nucleus is very dense. One thing I forgot to mention, the closer you are to the nucleus, the harder it is to remove that electron. The further you are from the nucleus, the easier it is to remove an electron. So these shells are divided into subshells. Subshells are designated by the letters S, P, D, and F. And within these subshells, electrons are grouped into orbitals. So let me go over this. We have our first shell here, shell number 1, right? Shell number 1 will have a 1s orbital, and it can have a maximum of 2 electrons. Shell number 2 can have 1, 2s, and 3 2p orbitals. So it will be maximum of 8 electrons. So if you we have 1 2s and 3 2p. So if we have, let me write here, we have 2s and we have 3 2p's, 2p, 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 right? So if you calculate, if you add those up, 2, 4, 6, 8, there you got 8. And then for shell number 3, we have 1 3s, and then we have 3 3p's, and we have 5 3d's. And each one, if you add them up, each one would have 2 electrons. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18. That's where you get the 18. And so on for shell number 4. Electron configurations of atoms are governed by 3 rules. These rules are: rule number 1, orbitals fill in the order of increasing energy from lowest to highest. Rule number 2, each orbital can hold up to 2 electrons with spin paired. Rule number 3, when there is a set of orbitals of equal energy, each orbital becomes half filled before any of them become completely filled. So let me show you here. For hydrogen, right, we have our orbital of 1s, which is one electron. We know that hydrogen is 1 electron, so we have 1 arrow facing up. And then we have helium, which is 2 electrons. We got this completely filled the box with an arrow going up and arrow going down. Those are your spin pairs. To write the hydrogen as an electron configuration, we see here it's 1s1, right? Then for helium, 1s, which is this box right here, right? That's the 1x box. For helium, which has 2 electrons, it's written as 1s2. You see it says 2 right there. Next example we have, let's do lithium. Lithium has 3 electrons, so we fill our first one, where our 1s orbital, right, is filled. Then we start our second orbital, which is a 2s. So if you see here, 1s2, that's 2 electrons. Then we have 2s1, which is another electron. So we have 3 electrons total. Let me go down an example here. Let's do oxygen. Oxygen is a good one. Oxygen has 8 electrons. So we first fill our 1s orbital up and down. Once we fill that, we go to our 2s orbital, right? We fill that. And then our p orbitals, we know we have 3 2p orbitals. So first we fill so we have 3 2p orbitals. We have 2p, 2p, and 2p. So first electron is filled in the first box, second electron is filled in the second box, third electron is in the third box. Then, once all boxes are filled, you compare them. The fourth electron is in the first box. So you can see that here. And for once all of them are filled, then you move on to your next orbital. So that's for sodium. Sodium has 11. Now you see how all 3 are paired, and then you go into the next orbital. One more thing I want to go over here is the noble gas notation. So once when you look on the periodic table here, let me clear this out for you guys. So we know helium has 2 electrons, right? When we get to lithium, which has 3 electrons, instead of saying lithium is 1 plus 2 plus 3, we can say lithium has the same characterization as helium plus 1, right? Or if we do, let's say, calcium, right? Calcium would be argon plus 2 electrons. So that's how the noble gas notation goes. So here they put helium, all of the helium and the neon for you. Then we have our Lewis dot structures. When discussing the physical and chemical properties of an element, chemists often focus on the outermost electron shell. And the reason is because these outermost shells are involved in chemical bonding, which cause chemical reactions to take place. So the outer shells of these electrons are called the valence electrons, and the energy level in which they are found is called valence shells. A Lewis structure is shown by the symbol surrounded by dots. The dots are the most outer shell, the valence shell. What did I miss here? It says the atomic symbol represents the nucleus and all filled inner shells. So, going back to here, let's say for chlorine, right? You know, you see all these are filled. This is filled. All these are technically the nucleus, and then this is the outermost shell, which has 2, 4, 5. So if we go back here to chlorine here, chlorine has 17 electrons. So we have the 5. I made a mistake here. The neutron is this, and then the outermost shell is this. So we have the 5 in the pink, and then the 2 in the blue here. The 2 here and the 5 here. So the 2 is the first shell that's filled, and then the 5 is the following. Let me go back. So for chlorine, I'm just going to draw here for you. Chlorine, we have 7 outer electrons. So first we will put all the 4 first, and then we will start pairing them. So it would be 3 pairs and 1 single. So this is the single, and then you got the paired ones. How are electron configuration and position in the periodic table related? Well, the periodic table works because the elements in the same column have the same outer shell electron configuration. So let me explain that in detail for you. Going back to the periodic table, we see here our halogens, right? 7A. Fluorine, chlorine, bromine, iodine, they all have the outer shell 7 electrons. So fluorine, we have 7. We have 1, 2, 3, 4, 5, 6, 7. Right? And then chlorine will be the same thing, right? 1, 2, 3, 4, 5, 6, 7. But we know that chlorine, the nucleus, is more dense, has a higher mass than fluorine. Going back to where I left off. This picture actually shows what I just mentioned. So you see here how hydrogen has just one, lithium also has one, sodium also has one. What is a periodic property? So ionization energy is the energy necessary to remove the most loosely held electron from an atom in the gas phase to form an ion. Ionization energy increases from bottom to top within a column, and it increases from the left to right within the row. So how I memorized ionization energy was, so we said bottom to top, right, and left to right. So the highest ionization energy would be found clearly to the right and to the top. So that would be to the top. Okay, it doesn't want to write. Going up and to the right. And here is like the highest. The last thing I'm gonna go over is size of an atom, atomic radius, which is determined by the size of its outermost occupied orbital. So this atomic size is a periodic property. For the main group of elements, the atomic size increases going down the group and decreases going from left to right across the period. And going down the column, the outermost electrons are assigned to their higher and higher principal energy levels. For elements in the same period, the principal energy level remains the same from one element to the next, but the nuclear charge increases by 1 unit because you're adding 1 proton. As a result of this increase across the period, the nucleus exerts a stronger pull on the valence electron and atomic size decreases. So an example, so we have a nucleus here, right? We have our first shell, second shell, third shell. So if our first shell is filled and our second shell is filled, our second shell can have maximum 8. And then let's say we have an electron here, right? So we get rid of this electron. What happens? We lose that electron, therefore all these other electrons will get closer to the nucleus and they will be very, very hard to separate. They will nearly not separate at all. And these completely filled electron shells are your noble gases. That's why the noble gases do not react there with anything, because all of their shells are completely filled. Okay, I know this was very detailed lecture. I'm not sure how much of it you guys went over in your lecture class. I think the problems I went over are very important to do your homework. If anything doesn't make sense to you, please email me and I'll try to explain it in more detail. I try to keep it as simple as possible because this is a general course, right? You're just gonna learn the basics here. I don't want to get into too much details. I don't want to confuse you guys. So like I said, if you have any other questions, just send me an email and I'll get back to you as soon as I can. And I'm going to end our lecture now.